Video 8 of the GCSE Physics series, and the topic is forces in balance. Now, we cannot talk about forces in balance without starting by talking about the difference between vectors and scalars, because forces, amongst other things, are vectors. So, first of all, let's identify what we mean by a vector. Define the word vector. A vector is a quantity that has a magnitude, that's a size, some indication of how big the quantity is, and it also has a direction, whereas a scalar is what we call a quantity that has no direction, just the magnitude part, just the size. So some examples of magnitudes are up here. A magnitude of a mass might be 3 kilograms, a magnitude of a distance might be 4.5 meters, a magnitude of a duration might be 25 seconds. So it gives you some indication of the size of the thing, the quantity. What we mean by quantity is a quantity is something we can measure, a variable we can measure. So some quantities have a direction associated with them and some don't. So down here is a table of different quantities, and the scalars are listed, and there are more scalars besides what's listed here, and the vectors are listed. And again, there are more vectors than what's listed here. So not included on this list would be things under scalars like potential or potential difference. Under vectors, we could have electric field strength, flux density, whereas we could have flux linkage as a scalar. So there's lots of quantities that we haven't included here. We've just picked some, so we get some idea. Sometimes you'll be asked to list some scalars or vectors, so it's good to have a small list in your head. So let's have a look down this list and think. Energy. Energy, that store of energy, doesn't have a direction associated with it. The same as mass, an amount of matter that an object has, doesn't have a direction associated with it. Now, an object that contains mass can move in a direction, but the mass itself, the quantity of mass, is not attached to a direction. It is just a scalar. Same with charge. We covered that in video 4 and 5, mostly video 4. Speed and distance, and sometimes you'll hear people, even myself, rather clumsily talk about directions associated with distances and directions associated with speeds, and of course that's wrong. The word distance, colloquially, that means in everyday English, means something different to what we mean as physicists when we say distance. So someone might say a distance as how far you would have to travel from where you are to where you're trying to go. That would be a distance. And so if I move towards my destination, then I am shortening the distance. And if I move away from my destination, I am increasing the distance. And that is what one might mean by distance colloquially. So I live a distance of around about 10 kilometers from my school. Actually, that's not quite true, but I'm not going to give away where I live, otherwise I'll get some sort of dox attack or something. So let's say I live 10 kilometers away from my school. Colloquially, we would say that the school is a distance of 10 kilometers from me, which means that as I move towards the school, that distance decreases, and I move away from the school, that distance increases. As a physicist, when I say distance, what I mean is the amount of space through which I have moved. So as I move towards my school, I am increasing the distance, because I'm increasing the amount of space through which I have moved. When I finally arrive at the school, I have travelled a distance of 10 kilometres, or thereabouts. When I turn around and come back, I continue to increase my distance, because I continue to move through space. No matter what direction, if we are moving through space, we are increasing our distance, the space through which we have travelled. And so distance doesn't have a direction associated with it. It is just an amount of space, which means you can never decrease your distance. Unless you can somehow go back in time, you can't undo space through which you have moved. That's what we mean by distance as a physicist. When people talk about distance, they're usually talking about the magnitude of displacement, colloquially, in everyday English. That's what people mean. The displacement is the one way of describing it would be the what we'd call colloquially distance, the space between 2 points, in a particular direction. So, again, don't want to get doxed, but let's just pretend that I was 10 kilometers south of my school, then my displacement, the displacement that I would undergo or experience or have when I move from my home to the school would be 10 kilometers north, because I live 10 kilometers south of the school. So that is a amount of space between the destination and the origin and the direction, 10 kilometers north. That is the amount of space between the start and finish point, which means that if I go to school and then come home again, my displacement is 0. I have undone the distance between my start point and finish point. My start point and finish point are the same point, so it doesn't matter how much space I've passed through, my displacement is still 0. So you can see there's a difference between these meanings, and displacement has direction. Speed, okay, that's the distance, the space through which we have travelled, divided by the duration of our travelling, how long we have been travelling for. That's what we call a speed. That doesn't have a direction associated with it. In my car, I have a speedometer or speedometer. As I'm driving forward, the faster I drive, the further the needle goes around. If I pop it in reverse and drive backwards, it also tells me the speed. It doesn't care that I'm going backwards and give me some sort of negative number. It just accepts that speed is the amount of space through which I have travelled divided by the duration of my travelling. And velocity is a speed, but in a direction. Or you could think of it as a displacement divided by time in a particular direction. Well, displacement has a direction, so the velocity has a direction too. So if I'm travelling 10 meters per second, that's a speed. But if I'm travelling 10 meters per second forwards, that is a velocity. 10 meters per second up, that is a velocity. 10 meters per second north, that is a velocity, because they have a direction with them. Acceleration you should have covered in Key Stage 3, the rate of change of velocity. Well, acceleration is a vector, because it's a rate of change of velocity. So it is how much our velocity has changed, final velocity subtract initial velocity, divided by the duration of that change, divided by time. So momentum and force, momentum we haven't really covered yet, so put a pin in that, we'll come to it later. But force, you can push something in a direction. So force has a direction. Well, now we've cleared that up, why are we so bothered about whether something's got a direction or not? It feels like an awkward add-on, like an inconvenience to talk about the direction. Well, it's because it matters. So let me explain to you why. When we add vectors, we have to consider the vector nature of the quantities we are adding together. So, for example, if I am adding a distance of 10 meters north to 5 meters south, I'm not going to get 15 meters. My displacement from start to finish, when I add those two legs of the journey together, well, I've gone forward, north, 10 meters, and I've gone south, I've gone backwards, 5 meters. So I've actually only gone 5 meters north. Now, we get this idea, and when we learn to count and we learn to add up, we actually learn to do that using a number line. That's how we learn it when we are younger, when we're in primary school. We draw a number line, and if we are adding a positive number, then we add a certain displacement, a distance in a certain direction. Usually that's to the right. Usually you have your numbers getting more positive to the right. Then, if you want to subtract a number, you add a distance, add a displacement, should I say. There we are, I tripped up. Add a displacement, but in the opposite direction, to the left. And that's how you go backwards on your number line. So you go forwards on your number line with positive numbers, backwards on your number line with negative numbers. And that's how you learn to add and subtract in primary school. And that's adding displacements. And if the displacement is negative, you're still adding the negative displacement, which is the same as subtracting the displacement. Okay, so that's what we learned in primary school. But that's on one dimension. That's along a single line. What if our displacements are not one-dimensional? So let's look at this diagram here. Let's imagine that I'm displaced horizontally, and then I'm displaced vertically.
Well, I'm starting here. I'm displaced horizontally, so I end up here, and then I'm displaced vertically, so I end up here. So my what we call resultant displacement, the resultant of any vector, is what you get when you add the vectors together. The resultant displacement is this one I've labelled C. So as a vector addition, which is a special kind of addition, as a vector addition, we're saying A plus B equals C. But obviously, the magnitude of A plus the magnitude of B does not equal the magnitude of C. That doesn't work. What if the magnitude of A is, let's say, 3, and the magnitude of B is 4? 3 plus 4 is 5. Now, I know what you're thinking. 3 plus 4 is not 5, sir. You've completely gone crazy. How dare you? No, hear me out. 3 plus 4 is 5 because this is a right-angled triangle. I haven't drawn the right angle, but I've drawn it as a right-angled triangle. This is a right-angled triangle, and so if I were to do 3 plus 4, by which I mean I'm going to start from the beginning of A and end at the end of B, then I am drawing a hypotenuse. And we can use Pythagorean theorem to show that the square of 3 plus the square of 4 must equal the square of the hypotenuse. Well, 3 squared is 9, 4 squared is 16, 9 add 16 is 25, and the square root of 25 is 5. So A plus B is C, 3 plus 4 is not 7, it's 5. 3 plus 4 is 5, there we go. But it's because it's a vector addition. So when you see things like C equals A plus B, that's a bit clumsy, but I have used bold letters to indicate that they are vectors that you're adding. But don't just think, oh, that's fine, I'll just add A to B, the length of A to the length of B to get the length of C. That's not how it works. Now let's take this resultant vector for a second, C. We've got a special name for what A and B are. Any vectors that you add together to make a resultant, we call components. So A and B are components of C. And in fact, because A and B are perpendicular to each other, A and B are perpendicular components. Perpendicular just means 90 degrees. So A and B are perpendicular components of C. C is the resultant of A and B. You see how these all tie together. So now we've got the idea that we're going to do a vector addition. How can we do that? Well, if it's a right-angled triangle, we could use Pythagorean theorem. No problem. It works. But what if it's not a right-angled triangle? Well, at GCSE level, what we then have to do is a vector diagram, a scale diagram. And this is the rules, the instructions that you follow on the top right. Let's take this question. Imagine I have a vector A, which is 3.6 newtons. Oh dear, it's not a displacement, it's a force. It's still a vector, doesn't matter. 3.6 newtons, and it's vertical. That's up. And we've got B, which is 2 newtons, and it's at 45 degrees to the vertical. What's the resultant of A and B? We're adding A and B together. Now, 3.6 plus 2 is 5.6, but the answer is not 5.6 because we have to do a vector addition. So, first of all, we decide the scale. Well, I know it's going to end up being less than 5.6, so I look at the available paper. Here's my available paper, and I think, well, I'm going up and to the side, so I'm going to make sure I start near the bottom of the page, so I've got plenty of room. And I think, well, 5.6, so let's start down the bottom. 1, 2, 3, 4, 5, 6. It's not going to go as high as that. That's near the question. So let's say 1 centimetre is 1 newton. We've picked a sensible scale. Number 2, draw the vectors as arrows. So using this scale where 1 centimetre represents 1 newton, in this case, could be a different scale, choose a sensible scale, I'm going to draw my 3.6 newtons as 3.6 centimetres up, and then I'm going to draw the 2 newtons 45 degrees to that afterwards, which means I've got to get a protractor out to make some measurements of angles. I need a protractor and I need a 30 centimetre clear plastic ruler. And how am I going to make sure that this length is my 2 centimetres? Well, I could just measure it with the ruler, or I could get a pair of compasses and draw a circle with a radius of 2 centimetres, and that'll help me. It doesn't really matter. And I end up here. Now, A plus B is this red one, A plus B. Vector addition, A plus B. I could also instead have done B, which is this green one down here, plus A. And B plus A is the same as A plus B. I start in the same place, I finish in the same place. So the resultant vector is represented here as this red arrow. Its length is 5.2 centimetres. I measured it with a ruler. And 1 centimetre represents 1 newton. So that's 5.2 newtons. That's the resultant vector. That's the resultant force. But force is a vector, which means I must give a direction. So I get my protractor out and I measure this, and it's 16 degrees to the vertical. So my answer is 5.2 newtons, 16 degrees to the vertical. That's it. That is how we add our vectors graphically. Students really struggle with this, but you don't have to. You just start from the beginning and draw the first vector and then start the second vector from the end of the first. Now, I'll put a note up here about trigonometry. If you knew what the resultant vector was and you wanted to calculate components and our angle theta was here, then you could use trigonometry. So the hypotenuse multiplied by the cosine of the angle between the adjacent and the hypotenuse is equal to the adjacent. So that particular component of our force vector. If it's force, if it's displacement, then displacement vector, or velocity, velocity, it doesn't matter. So I'll just leave this here. You shouldn't need to use trigonometry like this in your GCSE physics. I don't imagine it can come up. But it's good physics anyway. It's good to know how to use what you learn in mathematics, trigonometry, to answer problems in physics. In fact, that's why you do trigonometry and maths, is so that you can work with vectors in physics. It is the reason why. Well, that's the end of that lesson. Let's have a look at lesson number 48. That was lesson 47. So let's have a look at lesson number 48. Lesson 48. Forces between objects. Remember, this is all about forces in balance. So we need to understand what a force is. And at primary school, you may have been taught that a force is a push or a pull. And that was fine for primary school. Nothing wrong with that. It's not great, but it's not necessarily wrong. It's just a little bit lazy, you know. If force is a push or a pull, then what is friction? Well, that's a kind of push, I guess. Oh, it's not wrong. What about gravity? Gravitational force. Is that a pull? Well, not really, because pull is a contact force. And in fact, a pull is just pushing something from the other side. When you pull a door handle, your hand just pushes the other side of the door handle. That's not great, but okay. Force is a push or a pull. That's a good starting point. But then, unfortunately, not always. Some primary school teachers are fantastic, but some of them don't know a lot of physics. That's nothing to be ashamed of. They know a lot of things, and most of the world doesn't know physics, so they can be forgiven for not knowing things. But a lot of students who come from primary school arrive at secondary school and say, what is a force? What does a force do? Forces move things. No, that's Aristotelian physics. That is what was understood by Aristotle over 2,500 odd years ago. Ancient Greek Aristotle thought that forces move things. Forces don't move things. Things could be moving without forces acting. That is just the way it is. Forces do not move things. What a force does, or should I say what a resultant force does, if you have a resultant force, when you add up all the forces acting on your object using the vector addition we did last lesson, at the beginning of this video, if there is a non-zero value of that force, then it will cause a change in motion. I'm keeping motion quite vague at the moment. We'll talk a little bit more about what we mean by that later, but that's what forces do. They cause changes in motion. They don't cause motion. So I'll give you an example. Let us suppose we're on an ice rink. We're on an ice rink and we're on a bicycle. Okay, and not a bicycle, it's a bad example. A sledge of some sort. And someone gives me a push. Now, while they are pushing me, my motion is changing. I'm speeding up. When they stop pushing me, I don't immediately stop. I continue. and I continue sliding across that ice, even though the resultant force on me is 0, because I have no resultant force on me, my motion isn't changing, and I have motion. So why should my motion stop? If the resultant force is 0, there's no change in my motion, so I continue to move. Now, the reason why that works on an ice rink, but that doesn't work on my table or on the ground outside or something, is because on an ice rink, we have done a very good job of reducing friction to almost 0. Friction is what Aristotle didn't know about when he said that forces make things move. Friction is a weird sort of force. Now, there are a few sources of friction, a few ways that it works, a few mechanisms of friction. I'm just going to share this one with you. This idea that friction is caused by asperities, that's bumps and lumps on the surface, an uneven surface, these asperities interacting with each other. So we've got a top surface and a bottom surface, and let's imagine I am pushing the top surface with a force represented by this green arrow, and I'm going to ignore any vertical components of force here. So I am pushing this top surface with this green arrow at the top. And let's imagine the bottom surface is just saying where it is. Now let's zoom in on this particular diagram. So what can we see? Well, as I'm pushing this top surface, let us suppose that the top surface is moving at a constant speed from right to left at a constant speed. Well, if that's happening, this top surface here and this bottom surface here, at this picture, they are in contact with each other. And I've drawn a tangent to the point where they're in contact. That is a straight line that only touches that point of contact once between those surfaces. So there. Can you see that this top surface is going to be moving to the left away from the bottom surface? So there's no force between those two. And it's the same situation here. But here, the point where the lump at the top and the lump at the bottom are in contact is about here-ish, where my hand cursor is. And the normal is actually here. Not the normal, sorry, the tangent, this red line, is actually here. And if I do the same thing over here, here's my lump, here's my bottom lump. They're in contact about here-ish, where I've got my hand cursor. And so the tangent is this red line here. Now, contact forces, pushers, if you like, a push force, a contact force, also called a normal contact force. The word normal there, sometimes called a normal reaction force, the word normal there just means 90 degrees. 90 degrees to what? 90 degrees to the tangent. A tangent that passes through the point of contact between these two surfaces. So this green arrow is perpendicular to that tangent, and this green arrow is perpendicular to that tangent. Now, ignoring the vertical components of this green arrow, there is a horizontal component too. This green arrow has a horizontal component to the right, as does this green arrow, has a horizontal component to the right. And if I add the horizontal component of this arrow to the horizontal component of this arrow, they will have the same length as the horizontal component of this arrow, which is all of that arrow because it's just a horizontal arrow. Which means that, just horizontally, this force plus this force equals this force in magnitude. As a vector addition, the horizontal component of the left-hand force plus the horizontal component of the right-hand force plus this green force that I'm pushing it with at the top will equal 0. So these two surfaces are in equilibrium, the forces are balanced, and yet the top surface is moving. That's why there's friction. The top surface is moving. And what it means is it will move at a constant speed. I'm pushing it, and yet it's moving at a constant speed because of friction. Now, if I know the force that I'm pushing it with, I know the magnitude of the force of friction, the component of the force of friction that's horizontal. I know what that is because it's in equilibrium because I'm pushing it at a constant speed. And if I push it over a certain distance, then I can use my equation for work done that we did way back in video 1, which is that a force multiplied by displacement is a work done. And the force multiplied by the displacement would tell me how much energy is being transferred from the kinetic energy store of this top surface, which is what I'm putting energy into by pushing it. I'm removing kinetic energy out of that store at the same rate and putting it into the thermal energy store. That is what happens as I push this along at a constant rate. Just a reminder, lesson 3, video 1, had that equation for work done is force multiplied by displacement, and they were vectors. So we're only interested in the components of the force that are parallel to the component of the displacement to calculate the work that is done, transferring energy into the thermal energy store. Friction causes an increase in temperature. Okay, so let's carry on with this. We've now got the idea that friction is a contact force and it's caused by these asperities. Contact force. If there's no resultant force, there's no change in motion. That's actually another way of saying Newton's first law, which we'll cover formally in the next lesson, which is part of this video. What I want to focus on in this particular video, this particular lesson, is Newton's third law, because this is about forces between objects. And forces between objects is an idea that often gets very, very confused in students' minds. This is all about Newton's third law. Now, I'm going to say a statement that's going to make me feel very, very sick, but don't worry, I will hold my vomit in as I say it. Most people learn Newton's third law wrong. Most people learn it with the following phrase. Brace yourself, you'll very rarely hear me say this. Most people will learn... I'm finding it hard to do. Most people will learn that every action has an equal and opposite reaction. That was disgusting. That's what most people learn. There are problems with that phraseology. For a start, action means something particular in physics, and it's nothing to do with with this, nothing to do with forces. Secondly, action-reaction implies cause and effect. In other words, the reaction happens because of the action. Causality in physics is not instantaneous because of relativity. If you have an effect, then there's a time delay between that and the cause if they are separated spatially. And two forces will be separated spatially. It's impossible for the two forces to arise simultaneously in special relativity. So you can't call one a cause and one effect. Which one would be the cause? So that opens a whole can of worms with relativity, which we cover in year 13 physics, but not right now while you're doing GCSE. So what's going on with this then? Well, Newton's third law applies to forces that are arising simultaneously. So you can't really call one an action and one a reaction. It doesn't really make sense that way, which is why I don't like that particular phrase. Equal and opposite. That's the other thing I've got a problem with. If we assume that the person who said action equal, I don't want to say the whole thing again, it makes me feel too sick, but if we assume that what they mean is forces are equal and opposite, well, forces are vectors. So if two vectors are equal, they have the same magnitude and the same direction, because vectors have magnitudes and direction. So if forces are vectors, forces have the same magnitude and the same direction if we say that they are equal forces. So how can they possibly be equal and opposite? When people say opposite, they usually mean opposite directions. But you've just told me the forces are equal, which means they're the same direction. And now you're telling me that the forces are opposite, which means they're opposite direction. You're contradicting yourself. So it's no wonder students struggle in Newton's third law if they are taught it like that. It's the worst possible phrasing you could use. So I've got a whole rant about it, many rants about it on my YouTube channel. So let's focus on a better way of understanding Newton's third law. You can understand it in terms of 5 points. Actually, I think we should have 6 points because I like the idea of simultaneous forces arising. They arise at the same time as being a way of telling if two forces might be a Newtonian pair, a Newton's third law pair. However, because of the sticky stuff with relativity, which we're covering in year 13, we don't tend to include that on the list. So fair enough. Here are the 5 that you need to check. If you think two forces are a Newton's third law pair of forces, then you need to check, are the forces of the same magnitude? Are they the same type of force? So what do we mean by that? Well, a weight force pairs with a weight force. A friction pairs with a friction. Push pairs with push. The Newton's third law pair to the friction force is a friction force. Okay, that's the way it is. When I'm on my bicycle and I pedal, my tyres are exerting a frictional force on the ground, and the ground is exerting a frictional force on the tyres. They are the pair of forces. They're the same type of force. Gravitational forces pair with gravitational forces. That's the one that students really struggle with. Same type. Opposite direction. Forces have to be in the opposite direction, and number 4 is a point that students often miss as well. 2 and 4 students often miss. So acting on the other object, the forces act between two bodies. If you see two forces acting on one body, they cannot be a Newton's third law pair of forces. There could well be two forces acting on one body, but they will be paired. Each of those two forces will be paired with other forces, which aren't necessarily shown on a free body diagram. And I'll talk about free body diagrams just a little bit later. And the last point there, the forces have to act along the same line of action. That's easier to explain by way of a diagram. And I'll come to that with these diagrams along the bottom. So here are 3 examples of interactions of forces that are not Newton's third law pairs. And I've stripped the context away, so I'll explain it. Imagine I have a ball resting on a surface. I haven't drawn the surface. It's a free body diagram, so I haven't drawn the surface. I'm just representing the ball as this yellow blob. The ball has mass, and therefore it has weight, and therefore we can draw a downward arrow. The force is resting. The ball is resting on a surface, so the surface is pushing the ball up. That's a normal contact force up. And because the ball's motion is not changing, the resultant force is 0. So these two forces are going to have the same magnitude and be in opposite directions, so that the resultant force on the ball is 0, because it's not changing its motion. It's not moving, but it persists in a state of not moving, so its motion isn't changing. So now let's compare these and see if these two are a Newton's third law pair. Do they have the same magnitude? Yes. Are they the same type of force? No. This downward one was a gravitational force. The upward one was a push force, a normal contact force. They are not the same type of force. So that's not a Newton's third law pair. But let's just check the others. Are they in opposite directions? Well, yes. Are they each acting on a different object? No, they're both acting on the same object. Draw a line through it. It's not a Newton's third law pair. Are they along the same line of action? Yes. So if I draw a line connecting the point where each force is acting, then the forces act along that line. That is true. You can see that from this diagram. But they're not a Newton's third law pair. What does that mean? Well, that means that let's pair each of these off. The table, or whatever the surface this is resting on, is pushing the ball up. So the ball must be pushing the table down. And if I were to have drawn the table, I'd have to draw a down force on that table equal in magnitude to this up force on the ball, because the ball pushes the table down with the same amount of force that the table pushes the ball up. That's your Newton's third law pair. What about the downward force? Well, the ball experiences a gravitational force down. Okay, the ball experiences a gravitational force down. From what? What's the second body? It's not the table. The table doesn't have that much mass that is going to have a significant gravitational effect on the ball. No, the Earth, the entire Earth. So we would say that the Earth attracts the ball down because of gravity, so the ball attracts the Earth up because of gravity. And that's actually the same amount of force. So if I were to have drawn the Earth on this diagram, then I would have to draw a force arrow up towards this ball, as there is a downward arrow on this ball down towards the Earth. And they're both gravitational forces, and the lengths of those arrows would be the same, and so on and so on. But I haven't drawn the Earth, and I haven't drawn the table, so I can't draw the Newton's third law pair to each of these forces. But these two, just because they're same magnitude and opposite direction, does not mean they're a Newton's third law pair. Can you see why that vomit-inducing worst possible way of describing Newton's third law is a problem? If you just memorize it, as most of the world does, in the world out there, they're all wrong. If you memorize that, then you will get this wrong. Unlearn what you have been taught. Let's look at these two. Now, I don't know how this can possibly happen, but there's two balls. They're interacting somehow, perhaps. Maybe we've got two different forces acting on them, but maybe each of them is the same type of force in opposite directions, and so on and so on. But look, you can see because of the way I've drawn the arrows that they are not the same magnitude. So I don't know what these forces are. Maybe these are both... I don't know what they would be. Maybe this is a positive charge and this is a negative charge, and there's a big charge over here and a big charge down there, but that wouldn't produce these forces either. I don't even know how this would be possible. But let us suppose that somehow this is possible. They're different magnitude forces, so they're not a Newton's third law pair. And over this one, I don't know what's going on with the other situations, but those forces are not along the same line of action. You can see that. Draw a line connecting the 2 points where the forces are acting, and the forces don't lie along that line. So, no, I'm sorry, that's not a Newton's third law. I don't think these second two examples are even possible to make happen. Right, let's move on to the next lesson, lesson number 49. Lesson number 49, we're looking at resultant forces again. We've already covered resultant forces very briefly. I'll stop for a quick drink. We've covered resultant forces very briefly before. We know that we add forces together vectorially to calculate resultant forces. But once we've done that, what do we do with it? Why are we calculating resultant forces? And it's because Newton's first and second law are all about resultant forces. So here, I'm now finally stating all three of Newton's laws. Newton's first law, the idea that the resultant force, when the resultant force is zero, then the acceleration is zero. Acceleration is a better way of describing our change in motion at this stage. When we introduce momentum a bit later, we might find a different way of describing motion, but for now, this is fine. Acceleration is rate of change of velocity. Okay, so when our acceleration is zero, this is because the resultant force is zero. So the velocity isn't changing, and that's one way of saying the motion isn't changing. That's Newton's first law. But when the resultant force is something other than zero, when it's non-zero, when there is a resultant force, then the resultant force is directly proportional to the acceleration when the mass is constant. Now, in GCSE level, you're never going to deal with situations where the mass is not constant. That comes up in A level. Very interesting. When we get to A level, we'll focus on a better version of Newton's second law, where force is directly proportional to the rate of change of momentum, or it's directly proportional to the impulse rate. Change of momentum is the same thing as impulse. It's just another word for the same thing. I think you have to know that for GCSE as well. Impulse is change in momentum, but I'm sure we'll cover it later. So that's a better way of writing it, which we use in A-level quite a lot. But then after A-level, we get onto our degree and we realise that there's no way of having a change in mass without also having a resultant force. So you can't have Newton's first law expressed in terms of zero resultant force, therefore zero rate of change of momentum, where momentum is expressed, but where the mass is changing and the velocity is also changing in a way that cancels out. You can't have that. It's actually impossible. So you end up coming back to this equation anyway at university. But, you know, that doesn't matter. You evolve beyond this equation, you look back at it and think, gosh, that's babyish, and then you come back to it again at university and realise it was right all along. It's just the way it goes. So anyway, that's Newton's second law. Newton's third law, I've summarised it here as forces between two bodies always come in pairs. I can actually write a one-word, well, a very short, not quite one word, description of each of these. Newton's first law, another way of describing that is inertia. I nearly wrote the wrong thing. Let's just clear all that. Inertia. The tendency for a body's motion to remain constant unless you exert a resultant force. Then Newton's second law is all about rate of change of motion. So let's have impulse rate. So two words, not quite one word. And then the last one is about how forces between two bodies, so I like calling that interchange. So here I've managed to turn all three of Newton's laws into single words beginning with I. A lovely mnemonic. So you can always remember Newton's laws, I, the three I's or something. I don't know if that helps. Probably doesn't. So there's our Newton's three laws. Right, now let's focus on Newton's second law, because that's the one when the resultant force is not zero, and that's the interesting situation for us. So resultant force, we know how to calculate that. There's another way of describing resultant force, or defining it. Yes, it is what you get when you do a vector addition, adding of force vectors. But there's another way of describing it, and that's if you considered removing all the forces acting on a body and then just placing a single force that has the same effect, does the same thing, that is what we would say is the resultant force. The resultant force is this imaginary force that we can replace all the other forces with, and it does the same thing. It has the same effect. So if our forces acting on a body are unbalanced, like in this picture here, here is a free body diagram. This picture above is a free body diagram for the picture below. The picture below is not a free body diagram. So the rope is the dot. And we've got two people pulling on the rope, one with 200 newtons, one with 100 newtons on the left, and one person pulling on the rope on the right. That's with 200 newtons. And what do we find? Well, 200 plus 100, that is 300 newtons to the left, 200 newtons to the right. So the forces are unbalanced, that's what we say. If they're unbalanced, it means there's a resultant force. So what is the resultant force in this case? Well, let's say that to the right is positive, to the left is negative. So let's add these forces together. 200 plus negative 200 plus negative 100 gives us negative 100. So that's a resultant force of 100 newtons to the left. Or we could decide that left is positive and right is negative. Well, if left is positive and right is negative, then we've got positive 200, add positive 100, subtract, add negative 200. Not subtract, add negative 200, because it's to the right. So 200 plus 100 is 300, add negative 200 is 100, and it's positive, which we've decided is to the left. So either way, when you take direction to the right as being positive, or the direction to the left as being positive, it doesn't matter, it gives us the same answer. 100 newtons to the left is the resultant force, because there are unbalanced forces. If the forces are balanced, then the resultant force is zero. And that's not the case here. So when we have not an unbalanced force, or unbalanced forces, plural, then there's a non-zero resultant force. That is the F in this equation for resultant force. Then we can say that that is directly proportional to the acceleration, and mass is the constant of proportionality. And you explore this equation as a required practical, so I won't dwell on it too much, but it is a simple three-term equation where you can plug numbers in. And I've talked about what we mean by free body diagrams and acceleration I've defined already, so we're ready to move on to lesson 50. Lesson 50. We're going to take forces and we're going to park it to one side, and now we're going to start looking at turning effects of forces. One particular effect of forces. Turning effects. Another name for the turning effect of a force is the moment. It does have another name. It's also called the torque of a force. That's T-O-R-Q-U-E, torque. But we're just going to call it moment, because at GCSE level that's what they call it. At A level they do introduce the word torque. It means the same thing. So that's the turning effect of a force. Now we need to sort of understand what forces can do in terms of turning effects. And a PE GCSE does a good job of this by identifying three different classes of levers that all use the ideas of moments in their operation. That's GCSE PE, not GCSE Physics. You don't have to know the classes of levers in GCSE Physics. And in fact, I can never remember these because I never teach them, and it's just not that important to me. But levers are a way of using moments to either increase or decrease, is the case sometimes, but increase or decrease the force. And we're going to go into a bit more detail about how this works in this lesson. But that's what a lever does. I'm going to go straight to equations now, looking at the top right, because it needs some explanation, this equation. There's a lot going on here. And I'm presenting this in a way that is probably unfamiliar to students who have studied from their textbooks or from other YouTube videos or other sources of revision out there on the internet. They're coming to this video and they're learning about moments, and they see this bizarre equation for the first time. And isn't it interesting that in the previous lesson we had an equation where m and a are multiplied, and I didn't bother writing a multiplication symbol, but this time I have. Lesson 50, I've written a multiplication symbol. Isn't that interesting? It's also interesting that in lesson 3, video 1, when I did a multiplication symbol, I used a dot. And I made a little note back then that the dot means multiply when the product of these two vectors is a scalar. And I said, look, we'll talk about this later. Well, now is later. When we multiply a force by a displacement and the outcome from that multiplication is a scalar, we can call that a scalar multiplication, and we use a dot. Well, that's a force multiplied by a displacement, and we've got a force multiplied by a displacement in this lesson. I've written them the other way round, but that doesn't really matter. There's a displacement, there's a force. But this time I want to return a vector. The moment is a vector. The turning effect of a force could be clockwise, or it could be anti-clockwise. We even refer to these directions as clockwise and anti-clockwise in A-level, although when I teach A-level, I teach the moment vector a little bit differently. I teach it more correctly, but that it doesn't matter. You only need to know it more correctly for university physics, so clockwise, anti-clockwise as a way of describing direction of moment is fine. Oh, I should point out, moment is another one of these fun words where physicists took a word from the English language and completely changed its meaning. You say moment to people out there on the street, you say, what do you mean by moment? They'll think you mean a short interval of time. I'll nip in the shop, I'll just be a moment. Moment meaning a short interval of time. Well, what's going on at the moment? What's going on within this short interval of time now? Physicists, when we say moment, it's got absolutely nothing to do with time. Nothing whatsoever. We could have called it cabbages, the turning effect of a force. There's no reason to pick the word moment as though it's somehow linked to the colloquial meaning. It really isn't. So moment to us is the turning effect of a force. Just relearn the meaning of the word moment. It means something different now. And it is a force multiplied by a displacement. Now, the equation that you will probably be given by your teachers, by textbooks, by examiners, or whatever, is moment is equal to force times d. And sometimes they might even put an upside-down t next to the force, and sometimes they might instead put the upside-down t next to the distance, d. And they will use a d instead of an r. This is bad. It's not right. The reason they do that is because they don't want to confuse students by talking about a radial displacement, even though it's more correct. But if you are hoping to get marks in your GCSE examinations, then learn this nonsense. Moment is equal to the force multiplied by the perpendicular distance from the line of action of the force to the pivot. Perpendicular distance. Now, I've got a real problem with that, because distance is a scalar, so how can you have anything perpendicular to a scalar? Scalars don't have direction. Perpendicular distance doesn't make any sense. The reason they don't call it displacement is because students often think of displacement in terms of travelling from one place to another. The idea of there being a displacement without actually having any motion from A to B, but having a displacement AB, that idea some students can really struggle with. So, and I get it, I do understand why. So this is what you need to say, but perpendicular distance is nonsense. So here I've got R, which in your equation might be a D, and here I've got F. And you'll notice that F is not perpendicular to R. If F were perpendicular to R, I would get the maximum moment. If F were parallel to R, imagine I rotate F around so that F is parallel to R, then I get no moment at all. So what I need to do is resolve either my vector F or my vector R So I'm looking at a component of f that's perpendicular to r. That's why I've used the upside down t symbol, which is the symbol for the perpendicular component. So either f is perpendicular to r, or I can consider the line of action of f and choose a component of r that's perpendicular to that. And that's what you have there. Now, you can convince yourself by drawing various diagrams and making measurements, or just considering similar triangles, that theta, the angle between the perpendicular component of f, that's the component of f perpendicular to r, and f, theta is the same as this theta down here, the angle between r and the component of r perpendicular to the line of action of the force F. So those two angles are the same. We need to resolve our vector f to find the perpendicular component, or resolve our vector r to find the perpendicular component. That's what we need to do. And we can use trigonometry for that. So if we use trigonometry for that, to find this perpendicular component, we know that f perpendicular is f multiplied by the cosine of theta, because f perpendicular is the adjacent to the angle. Okay, this is a component, a perpendicular component. And we can do the same thing for r, and it would be the same thing. R, the perpendicular component, well, look, r is the hypotenuse. There's the right angle down here. R is the hypotenuse. So r perpendicular is r multiplied by the cosine of theta. And so what we can say is this equation, m, the moment, equals r cross f. We can simplify that. If we are representing the angle as the angle between the vector and the perpendicular component of that same vector, then we can simplify this equation by saying it is r, that is the perpendicular radial displacement from the pivot, multiplied by the magnitude of the force, multiplied by the angle, the cosine of the angle between the perpendicular components. Now that's fine. What happens if this angle is 0? Well, cosine of 0 is 1. That gives us the maximum moment. When f is perpendicular to r, we get the maximum moment. Because theta becomes 0, cosine theta is 1. What about if f is parallel to r? Well, then this angle becomes 90 degrees. And if this angle is 90 degrees, cosine of 90 is 0. So we end up with no moment, no turning effect. That's just the way moments works. Now, getting from this cross product, as we like to call it, this vector product, to this equation below, where you'll notice all the bold letters have gone because now I'm only looking at magnitudes. Going from the top equation to the next equation is A-level. It is complicated. But you do need to know for your GCSE that we are only interested in the perpendicular components of these vectors. And in the very recent exams that have happened, I don't know if it's the most recent one, that's only just happened this summer, but the one before that, certainly, there was a question, I think it was that exam, there was a question, just a qualitative question, where students had to answer, looking at pedals and students pedaling, what position the pedal has to be to get the maximum moment. And to understand what position, they have to understand this principle that you get maximum moment when the vector of force and the vector of displacement are perpendicular. So having an appreciation for this idea. So that's our equation for moment. Now we know how to calculate it. You want to make moment bigger? You make the force perpendicular to r. You want to make the moment bigger? You make f bigger. You want to make the moment bigger? You make r bigger. Any of those three things would make the moment bigger. Why do we call it r instead of d? Because we are considering rotation around a point, which means this point at the edge is going to trace a circle, and r is the radius of a circle. So that's why we choose r. That point around which we are considering rotation we call the pivot or the fulcrum. This could just be a beam, and so this might be a hinge that the beam is connected to, and that would be the pivot or the fulcrum. And we measure r from that point. So that if F is applied at that point, there's no moment. Okay, fine. So if this is rotating at a constant speed, if this black beam here is rotating around this circle at a constant speed, then we are in equilibrium. Textbooks get this wrong all the time. They will say that the moments are balanced, and we'll talk more about balanced moments in a bit, but the moments are balanced when the rotation stops. That is not true. We are balanced, in other words, we are in equilibrium. Moments are balanced, forces are balanced when motion, even rotational motion, is constant. So if this black beam rotates at a constant speed all the way around, I'm talking about angular speed here, but let's not get too complicated. This black beam rotates around at a constant speed, then the resultant moment is 0. So the sum of the clockwise moments will equal the sum of the anti-clockwise moments. And that's the critical point. If we look at a class 1 lever, let's imagine I want to rotate around this fulcrum, this beam, such that the heavy mass is elevated. Let's take the simplest case, which is the beam is rotating at a constant speed so that that rock is being lifted up. Let's take that very simple case. Well, in that case, the rock is pushing on the beam, and we call that force the load. Well, not quite. The rock is pushing on the beam, that's the load. The beam is going to push on the rock with the same magnitude of force, that's Newton's third law. Over here on the other side of the beam is where I push it, and we call that the effort, the force I am applying to the lever. And you'll notice that the load is closer to the fulcrum, to the pivot, than the effort is. So if we take this equation, well, actually, let's take this equation, or just the idea that we're multiplying that distance between the effort and the fulcrum. I'm just using the word distance now to keep it simple. Multiply that by the distance, by the amount of effort. That is the amount of moment in the anti-clockwise direction caused by the effort. If this beam is rotating at a constant rate, then the moment caused by the load must be the same, so that the resultant moment is 0. Clockwise moment equals the anti-clockwise moment. So if the effort multiplied by the distance between the effort and the fulcrum, that moment, is equal to the moment caused by the load, so that's the load multiplied by the distance between the load and the fulcrum, then this is rotating at a constant speed and we are lifting the rock up. But the distance between the load and the fulcrum is much smaller. So if I make the distance smaller to get the same moment, I have to make the force bigger. So that means that I get a bigger force applied at the load than I am applying at the point where I've written effort. I push down on this end with less force than I get out at this end. That's how levers work. They use what's called the principle of moments, which I will cover in a later lesson, part of this video. Right, so that is moments at work. We've got a good idea now about what moments can do, their use in levers, and how to use the equations to calculate moments. Brace yourself for lesson 51. We're now halfway, we've just gone past halfway through the GCSE course. And looking at this, you're going to think, ay caramba, that's complicated. It doesn't need to be. I don't know how advanced we need to go on this topic. Certainly, no questions I've ever seen asked in the current GCSE specification has gone into this sort of detail. But I think you should know it. So let us just have a look at this equation. Moment equals r times f. R is a radius. Fine. F is the force. Fine. Now, I'm pushing around this red gear. I don't know where, I don't know how, it doesn't matter. I'm pushing this red gear around. Maybe I'm twisting it around this black line, the axle, and I'm twisting it. It doesn't matter. That's me putting energy into this machine, into this system. We call it a machine. I'm going to zoom in at this point here for a second. Hopefully the animation will continue to run. Yes. At this point here, where the red gear is interacting with the blue gear, The red gear is pushing the blue gear down. The blue gear is pushing the red gear up. And I know that the blue gear must be pushing the red gear up with the same force that the red gear is pushing the blue gear down, because that's what Newton's third law tells me. Any force has a paired force. You just have to look at the objects that are interacting. Red gear tooth pushes blue gear tooth down, so blue gear tooth pushes red gear tooth up. So as the blue gear tooth pushes the red gear tooth up, that's trying to cause an anti-clockwise moment on the red gear. And I'm putting energy into the red gear by pushing it with a force which produces a clockwise moment. Now, because the red gear is rotating at a constant speed, whatever moment I am putting into the red gear clockwise is equal in magnitude to the moment anti-clockwise that the red gear is getting by being pushed back by the blue gear. So yes, this red gear is rotating constantly, but that means the resultant moment on it is 0. And I am giving the red gear as much moment clockwise as the blue gear is giving the red gear anti-clockwise. Students really struggle with this idea that the blue gear pushes the red gear back, because they'll think, but the red gear is not slowing down. No, exactly. It's staying at the same speed, which means the resultant moment on the red gear is 0. That's the point. So if the red gear pushes the blue gear with the same force the blue gear pushes the red gear, what does that mean happens to the moment? Well, the distance from the point of rotation for the red gear, that's the axle here, to where the force is acting, let's just call that r, the radius of the gear, that is the moment of the red gear. And for the blue gear, it's rotating around this point, this is the axle, all the way to here. So you can see that the radius of the blue gear is bigger than the radius of the red gear. But the forces each is exerting on the other is the same. So let's zoom out. So hopefully I don't zoom out so far that, yep, I've just zoomed out way too far. Where's that gear one gone? There it is. That's all the stuff we've got to look forward to. So we've got the same force because of Newton's third law at this point. So the force on the red gear is equal to the force on the blue gear. Just talking about magnitudes. They're not bold letters because I'm just talking about magnitudes. And if we rearrange this equation, then force is the moment divided by the radius, because that is the distance between where the force is acting and the pivot. So F equals m over r. And because F for the red one is equal to F for the blue one, then m for the red one divided by r for the red one is equal to m for the blue one divided by r for the blue one. And that's what I've written on this line. Now I can rearrange this to make all the moments on one side of the equation and all the radii on the other side of the equation, and I get that just dividing through by the moment of the blue one and multiplying through by the radius of the red one. And then if I took the reciprocal of this whole equation, I'd get this one here. So what is this telling me? This is telling me that because the radius of the blue one is bigger, the moment for the blue one must also be bigger. That's how this equation works. So this machine, red gear to blue gear, increases the moment. But by how much? Well, we could measure the radiuses, and the ratio of radiuses, radii, the ratio of radii will be the ratio of moments. So if the blue gear has twice the radius of the red gear, then the blue gear has twice the moment of the red gear, twice the turning effect. Okay, fine. Don't always want to measure the radius of a gear, though, do we? But we do know that the radius of a gear is proportional to the circumference of a gear, because that's the relationship between the radius of a circle and the circumference of a circle. And apart from the teeth, these are pretty circular. So the circumference, maybe I measure the circumference of the blue gear and the circumference of the red gear. And if the radius of the blue gear is twice the radius of the red gear, then the circumference of the blue gear is twice the circumference of the red gear. And so we could say that the ratio of moments is equal to the ratio of circumferences. But better than that, because the red teeth have to interlock with the blue teeth, we know that the teeth width are the same for the red gear as they are for the blue gear. So we can express the circumference in units of tooth width. And so because of that, the circumference is proportional to the number of teeth. So we could say if the blue gear has twice as many teeth as the red gear, then its circumference is twice as much, therefore its radius is twice as much, therefore the moment is doubled. The machine, which is the red gear to the blue gear, it doubles the number of teeth, so it doubles the circumference, so it doubles the radius, so it doubles the moment. That's how that gear works. Now let's have a look at the blue gear to the yellow gear, because this is a little bit different. Zoom out a little bit. Blue gear to yellow gear. Now you'll notice that the blue gear and the yellow gear are connected to each other. They're stuck together. They're probably the same piece of metal, just machined so that it's got these different parts to it. So because this is effectively one object, it's all rotating together, the moment of the blue gear, the turning effect of the blue gear, which currently is a resultant moment of 0, is the same as the turning effect of the yellow gear, which currently is 0. So the turning effects are the same. The moment of the blue gear is equal to the moment of the yellow gear. How interesting. So if they've got the same moment, then we can use our principle of levers again. Our principle of moments. Idea, not principle, that's a special name for something. Our idea of moments. The radius of the yellow gear is less than the radius of the blue gear, but the moments are the same. So let's zoom out. Oops, that's in. Let's zoom out. Hopefully I won't zoom out too far this time. One more step. There we go. So the moments are the same. You can see that I've written there, same moment. This is section 2. Moment of the blue one is equal to the moment of the yellow one, and moment equals r times f. Fine. Okay, so let us rewrite this equation then. We can say that rf for the blue one has to equal rf for the yellow one. Just like that. And we could rearrange this to put all the radii to one side by dividing through by the radius of the yellow one, and all the forces on the right-hand side by dividing through by the force on the blue one. Or we could do it the other way around, take the reciprocal of the whole thing. What is this telling us? It tells us the ratio of the forces is the inverse of the ratio of the radiuses. So if the yellow gear has half the radius of the blue gear, then the force at the edge of the yellow gear is twice as much as the force at the edge of the blue gear. And those two are going to be producing the same magnitude of moments so that the moment of the blue-yellow gear combined is 0. Okay? Red gear is pushing the blue gear anti-clockwise, like this, anti-clockwise. So red gear pushing the blue gear, yes, anti-clockwise. And then the yellow gear is pushing the green gear clockwise. I think I've got that right. Yes, I've got that wrong. So the red gear is pushing the blue gear clockwise. There we go. Look, as the blue gear pushes the red gear down, the red gear pushes the blue gear up. I knew I'd messed that up. So the red gear is pushing the blue gear clockwise, and the green gear is pushing the yellow gear anti-clockwise. And those two moments must be the same because the blue-yellow gear combined is rotating at a constant rate. So the moment resultant must be 0, so the magnitude of these moments must be the same. Okay. So what does that mean? Well, if the yellow gear had half the radius of the blue gear, the yellow gear has twice the force at the edge. So this machine increases force. It steps up the force. And then the yellow gear to the green gear is exactly the same physics as the red gear to the blue gear. So I won't go into that again. It's exactly the same. And you can chain together these gears as many times as you want. You can make it quite compact, and you can chain these gears together as many times as you want. And each time you do this, you're increasing moment and then increasing force, then increasing moment, increasing force, increasing moment, increasing force. So that by the end of this, you could have a considerable force. Now, I'm just going to compare the force I'm pushing this red gear with to the force I'm getting out of the green gear at the other edge. This machine increases the force by some ratio, and you multiply it up each time you go along. Does that mean it's creating energy? Well, no, it doesn't. It doesn't. Because remember our equation, we had that work done was equal to a force multiplied by a displacement. If I divide work done by time, and I divide the right-hand side by time, then I end up with work done divided by time is power, force multiplied by displacement divided by time is velocity. So I end up with this equation here. The power, the rate that I'm putting kinetic energy into the left-hand side of this machine, has got to be equal to the power, the rate that energy is coming out of the right-hand side of this machine. If this is a 100% efficient machine, which it won't be, but let's pretend it is for simplicity, then energy is conserved. I'm not losing any energy in this machine, so power in equals power out. And if that's the case, then how can I increase the force? Well, I have to decrease the velocity. And if you look at the edge of this gear on the left, the red gear, it's moving faster than the edge of the green gear. So it is not creating energy at all. I am getting more force out, but at a cost of speed. This means that if I want to lift a car up, if I have enough gearing, I could just push a gear around with my little finger, and as long as I push the gear around enough times, I could actually lift the car up. Obviously, I'd have to push the gear a lot of times around, because I'm not strong enough to lift the car up without the gearing system. So a little bit of terminology then. This is referred to as gearing down. Okay, we're lowering our gearing rate. It's a lower gear over here. So why is that? It's because we are lowering the speed that the edge is moving at. But in doing so, it increases the force at the edge, and as I've already said, it also increases the moment. If you're on a bicycle and you're setting off, then you are trying to accelerate up to some speed. You need to push yourself off. You need a lot of force to push yourself and get yourself moving. So you need low speed, high moment. So you start cycling at a low gear. And then as you get faster, you gear up. You increase your gear to a higher gear, so the gears are moving faster. But you don't need to push yourself as hard, because all you're doing is pushing against air resistance to keep going at a constant speed. So you can have a lower moment at the edge. If you're in a car and you're on ice, you like setting off in a higher gear, because there's no point having a low speed and high moment, because all that's going to happen is the wheels are going to spin all over the place, because there's very little friction, very low static friction. So you need to actually have a lower moment to set off if you are trying to set off in a car on ice. I think that's everything I need to say about this. I haven't mentioned chains. So chains or belts, you can connect two gears together with a chain. The only real difference there is the force on the edges are still the same, because the chain is transferring the force from one gear to the other, but the gear wheels rotate the same way when they're connected with a chain. That's the only difference. Okay, let's move on to lesson 52. It gets a little bit easier for the rest of this topic. So centre of mass, sometimes it's called centre of gravity, although centre of gravity is not the same thing as centre of mass. At A level, we'll learn the difference, but at GCSE level, they're synonymous. So if you hear people talk about centre of gravity, we mean centre of mass. For a nice regular shape, the centre of mass is going to be in the middle, where the lines of symmetry intersect. So what is centre of mass? Well, it's a really handy point where if we consider the weight to all be acting from that point, the physics works out as we observe. So obviously the weight isn't all acting at this point, because there's lots of bits of mass distributed all over this object. So it's not true that the weight is all acting at the centre. If I cut it up into little bits, the other bits aren't all weightless and all the weight's in the middle. But if I forget that and I say this is one body, I'm not going to cut it up, and let's imagine the weight is acting at the centre of mass, the physics works out exactly the same as what I observe happen for reality, so it makes it easier. Another way of defining centre of mass is the point where you can imagine all the mass is concentrated. Again, it isn't actually concentrated there. In fact, the centre of mass could be a point. Take a donut, the centre of mass is in the hole, isn't it? It's right in the middle. There's no mass actually there. But that is the centre of mass, the point at which we can think of the mass being concentrated.
but it's not actually. So this is the idea of centre of mass. How do we find the centre of mass? We can do it for geometric shapes, or regular geometric shapes, by drawing lines of symmetry. And if you've got a line of symmetry and it's a nice regular geometric shape, then there's as much mass on one side of the line as the other. And where these lines all intersect, that point is the centre of mass. Fine. But what if we've got an irregular shape? Well, then we're going to have to use gravity. And you pivot the object from one point. So here I've got, let's get my pen out. Here I've got a little hole. Imagine I'm pivoting it at that hole. Then what have I got? Well, I've got the centre of mass here. There's the line of action of the force. And I've got a perpendicular displacement r. And I've got a force F. And r times by F is equal to the moment. Sometimes I prefer to use the letter tau for moment because it means the same thing as moment is torque. And I've heard this letter pronounced as tor before, which is awful. It's tau. It's the Greek letter tau. I often use that for moment as well. But don't worry about that. That's just me saying that for completeness. So if I've got line of action of a force here, and I've got my r here, then I've got a moment which is clockwise. A turning effect. So if the object is initially stationary, and I let go of it so that the moment on it is not balanced, then it's going to start to rotate. And it will swing around and it will swing backwards and forwards. And because of friction at the point, at this pivot, it's going to lose energy from its kinetic energy stores. Eventually, it's going to settle with the centre of mass directly beneath the pivot. Now, if I drop a plumb line down, that's just a string with a heavy mass called a bob on the end of it. If I drop that down so I know what is directly vertical beneath the pivot and draw a line along that plumb line, I know that the centre of mass is somewhere along that line. Then if I do the same thing from a different point, I will then have two lines, and where they cross, the centre of mass is found. And that's what these instructions say. You can read them yourself. Some terminology. When we say freely suspended, we mean that we just let go of something and allow it to swing around. When we've got all forces we're holding it with removed, it's going to swing around. Eventually, it's going to return to its equilibrium position, where the centre of mass is directly beneath the pivot. There is an equilibrium where the centre of mass is directly above the pivot. That the moment's zero there as well, but that's unstable. Any slight movement, any slight perturbation causes there to be a moment which increases the turning effect, which causes rotation, increasing the turning effect because it increases the distance, which increases the turning effect, increasing the distance, and so on. It's like balancing a pencil on its tip. It's unstable. Although technically it's an equilibrium point. Well, it is an equilibrium point. It's an unstable equilibrium. We've got the centre of mass directly beneath the pivot. That's a stable equilibrium. Don't think I need to say anything else about centre of mass. No, I think I said everything I need to say about that. So let's move on to lesson 53. Lesson 53 is not a big one at all. This is usually a practice lesson in my classes where we work through some problems. We know what equilibrium is. Yes, it's where the resultant force is zero. The vector sum of forces equals zero. But also the resultant moment is zero. So there's no change in motion in terms of translational motion. That's moving left, right, up, down, in, out. And rotational motion. There's no change in rotational motion. So if we're rotating, we continue to rotate at a constant rate. If we're not rotating, we continue to not rotate. Now, we introduce the principle of moments. We've already met it, but we're going to introduce it formally now. When asked what the principle of moments is, one second. When asked what the principle of moments is, very often I will see students answer, principle of moments, force multiplied by perpendicular distance. And they pat themselves in the back and they think they've got it right. No, what you are doing there is defining moment. Principle of moments is not the definition of moments. It's something different. The principle of moments has two parts to it. The first part is that it applies to objects in equilibrium. Don't forget that. It's important. The second part is that when bodies are in equilibrium, the magnitude of the sum of the clockwise moments is equal to the magnitude of the sum of the anti-clockwise moments. Now, these three examples, for simplicity,
There's only one force causing clockwise moment and one force causing anti-clockwise moment in each picture. Now, actually, when we do this in lessons, I will go further than that, put multiple forces on it and all the rest of it. We get very good results in my school. I push students much further. But let's just stick with this simple picture to introduce this idea. It's only a summary. Let's look at this picture. We've got 12 newtons acting on the beam on the left, 11 centimetres from the pivot, and it's going to be causing a clockwise moment. The anti-clockwise moment, which will balance it, is caused by a force 16 centimetres from the pivot, but I don't know what the magnitude of that force is. Now, handily, the angle between the force and the beam is 90 degrees in each case, so these are nice. I don't have to do any trig here. So the clockwise moment is 12 newtons times 11 centimetres, 132 newton centimetres. Fine. The anti-clockwise moment has to be the same, 132 newton centimetres, and I calculate it in the same way, force times 16 centimetres, but I don't know what that force is. But now I've got an equation. If force times 16 is 132, then force is 132 divided by 16, so 8.25 newtons. And if you've got multiple sources of clockwise moment or anti-clockwise moment, laying it out in a table and adding up the sum of them at the end of each column, and they must be the same, is a really handy strategy. So you can see I've done the same thing here to find the missing force here. This one over here is a little bit more complicated because this 6 newtons is at 45 degrees. I've decided to resolve it to find the perpendicular component of this 6 newtons by doing the sine of 45 degrees. Nicely, the sine is equal to the cosine of 45. So if you remember a couple of lessons ago, I showed you an equation where I had the cosine in it, and this was the angle I was given. But I'm being given a different angle this time, so I've got to use my brain, I've got to think about it. Although, if I get it wrong in this case, because it's 45 degrees, sine of 45 is the same as the cosine of 45, so we're lucky on this one. In other cases, we won't be so lucky. We've got to be careful to think about the trigonometry. I'm after the perpendicular component of the force. So 6 times the sine of 45 times whatever this d is, I don't know what that is, has to be equal to the moment clockwise, which is 78 newton centimetres. Newton centimetres, not newtons per centimetre, newton centimetres, because we're timesing a force in newtons by a displacement in centimetres, newton centimetres. If the displacement was in millimetres, newton millimetres. It doesn't matter. If the displacement's metres, newton metres. Anyway, we can do the maths. We end up with 18.4 centimetres. Nearly there. 2 lessons left. Parallelogram of forces. We've met this already as well. So this should be nice and quick. Lesson 54. You've got to practice this. This takes a lot of practice. You need a 30 centimetre clear plastic ruler because you might have to draw a vector diagram diagonally across an A4 piece of paper, and then you might find that your 15 centimetre ruler is just not long enough. You need a protractor as well. Don't rely on your exams officer to have a supply of spare protractors. You need to have your own protractor. We've seen this example, so you know what to do, but you'll also notice that the green and blue shapes form a parallelogram. So we could, in our scale diagram, just think about drawing that parallelogram. So A plus B, then do B plus A. Remember, A was 3.6 newtons vertical, B was 2 newtons, 45 degrees to the vertical. So we did our scale diagram, and we ended up with a parallelogram, and we just connected from the beginning to the end. It's not always along the longest length. Never connect the end of one arrow to the end of the other. It's always start to end, not end to end. It's a very common mistake. So here's another example of us using the parallelogram of forces. Here's a car being towed with 2 tow ropes connected to the headlights, apparently. Weird. So here's a car being pulled along. There's a force acting on this rope here, the top force attached to the right headlight. That is this 2,000 Newton force drawn in blue. Look at the direction. The force attached to the left headlight, this diagonal force here, is the red one. Look at the direction. And if they are both 2,000 newtons, then what is the total force, the resultant force we're pulling this car with? It's not 4,000 newtons. It can't be, because these vectors are at an angle. So it's 55 degrees between them. We draw our diagram, 2000, 2000 with 55 degrees between them. We know that it's a parallelogram, so that's going to be 55 degrees at the other end here. Okay, 360 degrees, subtract 110 degrees is 250 degrees. Half of that is 125 degrees. So we know this is 125 degrees here and 125 degrees here. I didn't write any of that down. I just did some basic geometry in my head. I know the angles in a parallelogram add up to 360 degrees. I know that if this is 55 degrees here, then there's 55 degrees here, and 55 add 55 is 110. I know that 360 subtract 110 is 250, and so these two angles added together must make 250, so each must be 125. Hopefully I've got my maths right there, because arithmetic is not my strong point. So while I know what those angles are, I whip out my protractor, whip out my ruler, I draw that parallelogram, and then I add my arrowheads. Oh, you must have arrowheads. Do not forget to draw arrowheads on your vectors. You will lose marks if you don't draw arrowheads on your vectors. They don't have to be drawn on the ends. Look, it gets a bit messy at the end when all the arrowheads are crossing over each other. You can draw the arrowheads partway along the lines. That's fine, but you must draw arrowheads on your vectors. Then, being really careful to think about what force we're adding to what, draw your diagonal. Don't go across like this. Once you've drawn your arrowheads, it's really easy to see which diagonal to do from the start to the finish. So they both start from here, they both finish here. So no matter which way we go, diagonal across here. Don't go across like this. That's obviously wrong. And then you measure the distance using your scale, and you get 3,548 newtons in this case. You could solve this using geometry and trigonometry, making a whole bunch of right-angle triangles and finding perpendicular components and adding those components and so on. And we do practice that in my class at GCSE level, but I don't think that's ever going to be examined at GCSE level. I think that is just for A level. But I teach, always teach at this level and then get examined at this level. It's the right way to do things. But you do need to practice that. And if you want to get lots of practice with this sort of thing, loads of questions on Isaac Physics, or I've got a drill spreadsheet which you can download from physicswithkeith.com if you are an enrolled subscriber, if you or an enrolled tutee, should I say, who take part in my weekly tuition sessions. If you're not, then it is available on TES. I sell it for a dirt cheap price, or just contact me and I'll probably send it to you for free anyway. I don't care. Question generator that produces lots of questions you can practice. Anyway, look, here's the instructions. You do that yourself. Pause it if you need to. Follow through. That's how you do it. Next, last lesson of this topic. Last lesson of video 8. Forces in balance. Lesson 55. There's almost nothing for me to say here because we've done it all. Resolution of forces. This red force arrow is the same as this, is the same as this. Some optical illusion makes you think they're different, but I did copy and paste them. They are exactly the same. Those three forces are the same force because they have the same magnitude and they're in the same direction. Therefore, they are the same force. I have drawn perpendicular components for this one on the left, a different set of perpendicular components on the one in the middle, and yet another different set of perpendicular components on the right-hand one. If you are given a question, for example, there's a ramp and there's a car on the ramp and you want to know the acceleration of the car down the ramp due to gravity, and so you've got to think, right, I need to resolve my forces. My weight, my gravity force is down and the road is pushing me perpendicular from the road. I want to add those two forces together. Oh, crumbs, I need to know what the component of weight is that is parallel to the ramp. Then you can choose perpendicular components. One of them that is parallel to the ramp, parallel to the weight, one that's perpendicular to the weight, and the resultant, which would be down the ramp. No, that's back to front. The resultant is the weight, and then you choose components that are parallel to the ramp and perpendicular to the ramp. There we are, that's the right way around. The reason why you choose the hypotenuse as being the weight is because no component's ever going to be bigger than the weight. That would be impossible. You can't have a ramp and all of a sudden it goes down it faster than it would if it were just free falling. So the hypotenuse would be the weight, and then you would find components which are parallel to and perpendicular to the ramp. So you choose your components. And I've done the same thing here. Look, blue arrows here are all exactly the same length, exactly the same direction, so they are the same vector. And I've chosen 3 different sets of perpendicular components. So that's the first thing. You choose your perpendicular components and make it sensible. The second thing is when we are using trig, don't just reach for equations. You've got to be careful. You've got to use your brain. Students love equations because they're easy. Once you've mastered them, and memorizing things is the bottom of Bloom's taxonomy. It's the easiest of skills, is memorizing stuff. Everyone knows all 151 Pokemon. There are no more. I refuse to believe in any more Pokemon. Well, Silver and Gold were pretty good. 251 Pokemon. There are no more. Sorry, I digress. Apart from... people can memorize stuff. They can easily memorize lyrics for songs and things like that. Memorization is an easy skill for most people, not for everyone, but if you work at it, you can improve it. So people like equations. People like, oh, I know that equation, I'll grab it. And so they try and memorize whether it's sine or cosine. Now, you've already seen, not being too critical, you've already seen that here we chucked a sine in here and we had the angle 45 degrees back with that lesson. You also saw that here I expressed the equation with a cosine because the angle that was given was a different angle. So whether I used a cosine or a sine depended on the triangle and where the angle was. So let's look at these two situations. The purple forces, F, are exactly the same magnitude, same direction. I've got the same set of perpendicular components, these horrible brown arrows. But I've got 2 different angles I've chosen. Theta, this one here, or gamma, this one up here. Now theta, if you know what theta is, and you know what F is, the resultant vector, then this component is the adjacent component to the angle. So that's hypotenuse multiplied by cosine of theta. And this is the opposite of the angle. So it's the hypotenuse multiplied by the sine of the angle. Whereas this one, because I've got the other angle, this is now the adjacent to the angle. It was, over here, the opposite to the angle. Now it's the adjacent to the angle. So that's going to be the hypotenuse multiplied by the cosine of the angle. And this one, which before was the adjacent to the angle, is now the opposite the angle. So that's now the hypotenuse multiplied by the sine of the angle, gamma. Okay, so you've possibly done various mnemonics to remember your trig functions. I don't know what they might be. Some people write horrible things. Really does... Ugh. Come on, pen, start working. Let's get my pen selected. Some people do horrible things like sort of this. Oh, it's awful. I don't even know if I want to finish it. The reason why that's so horrible is because what they are basically doing is writing a whole bunch of formula triangles. Blah! That's another thing that makes me vomit. Don't need formula triangles, just learn algebra. Whatever helps you remember trig, though, at first, knowing this sort of thing equals opposite over hypotenuse, knowing this sort of thing is a bit weird. So any mnemonic that helps you learn that is fair play, I think. By the time you get to A level, you won't even have to think about trig. You just use it without even thinking about it. It's just automatic to you, whether it's sine or cosine of an angle. You just know. You just know it. You don't need to think about it. And that's it. That is the end of this video. It's been a long one, over an hour and a half. It's been a long one, but it's had a lot to cover on forces in balance with a whole bunch of stuff on vectors in there as well. Hopefully you found that very useful. Do let me know. Thank you for tuning in and sticking with it for an hour and a half. The weekly tuition sessions will be carrying on during term time. That's very different to this. They are interactive. I've said it many times on the ends of these videos. They are interactive. It's very different. You're not just sitting there watching a video for half an hour, 40 minutes. It's, it's proper tuition where you get to answer questions and ask questions and there's interactivity. If you're interested in that dirt cheap price, just contact me, let me know. I'll do it for free to people who can't afford it. You just got to let me know, just talk to me. It's all about helping people. So enroll on the website, physicswithkeith.com. Thank you so much for tuning in. Take care of yourselves, and I'll see you on the next video.
Just a bonus message at the end to see if anyone actually stays and watches till the end. The first 5 people who comment below and say, yes, I've watched till the end, and contact me and let me know, I'll send you a free badge. Ooh. Or not. I might not, because I might not be able to afford it. First 5 people, let me know if you've got this message. Free badge. Bye.